Hey guys, it's Coach Fran here. What we're going to be talking about today is showing you guys a different equation in a different form of a quadratic that's going to represent the exact same picture that we've been dealing with. Everything we've been talking about thus far has been dealing with a form that we've been calling standard form. Okay, now standard form we've been pretty familiar with thus far has been ax squared plus bx plus c. Now, quadratics really aren't that much different idea-wise from linears. Whereas linears last semester, what we talked about was a linear equation had multiple different forms that you could write. You could write a point-slope form, a slope-intercept form, a standard form. Hopefully these things sound familiar to you. And all of those different equations represented the same line. The same concept goes for a quadratic. There is a different form that I can use to write the same quadratic. The equations look different, but the pictures are going to be exactly the same. Okay. So we're going to get more intimate and more familiar with this vertex form over the next coming weeks. So really introducing it today and just showing you guys this easy intro this week of what it does and how it really changes in the standard form is going to be important. So today in particular, what we're just going to talk about is pretty much the same thing we did last week, which is using a vertex form, which is still a quadratic. We're going to get all of the key features and we're going to graph the exact same picture. Okay. But then what we're going to show you is really to support how both of these two equations pretty much are the exact same thing. I'm going to change a vertex form into standard form today and show you how one form can turn into the other, which is going to be pretty neat. And then we'll be playing around with vertex form over the next couple days and show you how it can do a lot of cool things as well. So really, we're going to start off with what you guys know how to do already. Let's use Desmos to graph this quadratic. Why don't we? Okay. So I already have it preloaded into Desmos for me. Okay. My second line, which is my second example, is hidden. So really what I'm focusing on right here is example 1. So what you can probably notice is I can still get all of those key features that we talked about last time. I can get the vertex, a y-intercept, and I have 2 x-intercepts here. So what we're going to do is we're going to fill out my graph or fill out the key features from my graph. So looking at this obviously opens up. The vertex, which is always the bottommost or the topmost point, is -1, -4. And being that it opens up, my vertex is at the bottom, which means it's a minimum. And I'm just going to check that box to tell you it's a minimum. Now, like we talked about last time, the axis of symmetry is the same thing as the x value of our vertex. Okay, so if our x value of our vertex was -1, my axis of symmetry is x equals -1. So I'm going to graph this picture on my notes as well, so that I know where my vertex is, -1, -4. Okay. My axis of symmetry, I'm going to use a highlighter and color it with a particular line, just so I know this is the line that is going to cut this graph evenly in two. So everything on either side of that line, okay, should be symmetric, which is why it's called an axis of symmetry. Now, from my picture, my y-intercept is 0, -3, which I can plot, 0, -3. So if I have this point over here, and it's one tick away from my axis of symmetry, I know I have a symmetric point right on the other side of that axis of symmetry, one tick away from that. Okay. So my x-intercepts, I have 2 of them in this case. One of them is 1, 0, and one is -3, 0. And I can plot both of those. 1, 0 and -3, 0. And what you'll notice to really continue to support that idea is each of these points are 2 values away from the axis of symmetry, telling me that they are symmetric or equal distant from that axis of symmetry. So really from here, what I can just do on these notes is I can now just draw that graph. Okay. And it mimics what I have on Desmos. Now, the domain of every quadratic, like we've talked about, is that weird R sign, which hopefully you guys know means all real numbers. The range, which is Y, we talked about that little trick last time on where does the inequality go, which direction. So just as a quick reminder, okay, for the inequality, if it opens up, the inequality opens this way. If it opens down, it opens the other way. And the way that we kind of talked about it, or that little trick I showed you guys, is this creates the word up, or makes the letter P in particular, and the other one makes the letter D for down. Okay, so that should help me with this inequality, which it's obviously that way. Now, being that it's range, I have a lowest or a highest point. So which do I have here? If it's opening up, does this graph stop going up or does it stop going down? It stops going down at a particular point. And that particular point is at my vertex. And what we discussed last time was that the vertex is always used in my range, or in particular, the Y value of my vertex is that Y value is going to go here, which is a nice little thing to remember because you'll look at it is at this point here, that's the lowest point of my graph. So that Y value is what I'm going to use, which is -4. And then I'm done. So really, nothing new necessarily, right? Hopefully you agree with me. There's nothing new with this. It's just a different equation that creates the exact same shape of what we've done before. Okay. Which should make example 2 really easy. So I'm going to hide this first example, and then let's mess with the graph that I'm messing with now. Negative x plus 3 squared. So looking at this guy, what we'll notice here, okay, is I have a couple things that I'm messing with, okay? So let's answer the easy stuff right now. It opens down in this case. My vertex is my maximum because it's opening down, because it's the highest point, is at -3, 0. Now I'm going to stop here. If that's at -3, 0, what is my vertex also in this case? Look at where the vertex is on this graph. What axis is it on? The x, which means my vertex is also my x-intercept. So I'm answering 2 questions with 1 point, which is nice. Now, like we've talked about, my axis of symmetry here is x equals -3 because the y value, or the x value rather, of my vertex is -3. So that's where this number came from. This number came from here. Forgot to highlight it last time, just so you can see the relation. Awesome. Going to use the same green. And this is that line that's going to cut this graph evenly in 2. Okay. Now, I do have a y-intercept at 0, -9. 5, 6, 7, 8, 9. Just all the way down there. So now if I have a point there, this y-intercept is 3 ticks away from my axis of symmetry, which means I have a point 3 ticks on the other side of that, being symmetric. Now, looking at this graph, where would be some good points that we might use? Okay, you might want to ask yourself. So I'm looking at my Desmos graph, and I see that I have points at -2, -1, and on the other side of that. I'm just seeing right where that graph crosses at nice areas. Okay. So that line looks like it's also crossing at -1, -4. I notice that because as I'm looking at it, about right here in this spot, my graph is crossing that T of my 2 grid lines pretty nicely. So if I have a point there, go to the exact opposite side and copy that point because they should be symmetric. And my graph looks pretty identical to what I have on Desmos. Now my domain here is all real numbers. The range is going to open up to the right this time because it's opening down. And since it's opening down, okay, and it's a maximum, I'm still going to use the y value of my vertex, which is 0. Because that y value at 0 is the highest point on this graph. It doesn't get any higher than that, which makes my life easy. Nothing new, really, right? Hopefully you agree. But now showing you that this form, vertex form, which I've given you the actual official form, okay, with the letters, and we'll get more into the letters next week's lesson. But I really just want to show you that the vertex form and the standard form can represent the exact same line, which is pretty nice. So I'm going to delete these. What I'm going to do is I'm actually going to graph this vertex form on here. I'm going to do, before we get started, let's do y equals, let's go x plus 6 squared minus 1. So I'm not getting key features. I just want to show you the picture because what I'm going to show you is that when I change it to standard form, or when I change this equation to standard form, I'm going to write that standard form here in Desmos as well. And my equation should be the exact same, or the graph should be identical, meaning they're equivalent equations. Just because they look different doesn't mean that they're actually different. So if you notice what I put is to change our vertex form into standard, I have to simplify the equation, which means I want to get rid of all the parentheses. I want to combine all my like terms and just get terms in an equation that I can't combine anymore. Okay, there should be nothing else in the problem that I can combine or multiply or distribute, all that stuff, which is really us following our order of operations, also known as PEMDAS. So that's what I'm going to follow here. So for this vertex form, P for PEMDAS stands for parentheses. There's nothing in the parentheses here for me to work out. Okay. E tells me exponent. So I'm asking myself, is there an exponent here? Answer is obviously yes. So since my exponent in this problem is 2, I have to look at this guy because all of this is raised to the power of 2. Okay, we've talked about this in our square root method lesson. I know everything's raised to the power of 2 because there's parentheses. That parentheses is surrounded by the x and the 6. Okay. So how do I work that out? Well, if you think back, anything that is squared is really just that base, which is x plus 6, multiplied times itself 2 times. So x plus 6, if I break that apart, is x plus 6 times x plus 6. And that's just me simplifying that out. Okay? And then the minus 1 is just going to carry. So I'm getting rid of that exponent by separating x plus 6 squared into 2x plus 6's. Those two things are equivalent. Now, in PEMDAS, P-E, M for multiply. Is there anything here that's multiplied together? The minus 1 is not multiplied, okay, because it's subtracted. But these two guys here are multiplied together. So what I have to do is to use a double distributive property. So, or you can use box method, whatever you like to do. So we're going to multiply these two guys out. X times x is x squared. X times 6 is 6x. 6 times x is 6x plus 36, which then this simplifies to x squared plus 12x plus 36. And that minus 1 still comes down. I haven't messed with it yet. So now, PEMD, division. Is there division? No, there's not. I see no division sign, so we can skip that. A, addition. Is there any addition in this problem? Yes, there is, but I can't add these three terms together because they're all different. Okay, you can only add x squareds with x squareds, x's with x's, and constants with constants. Oh, but I do have two constants that I can, leading to my last letter, S, subtract. I can subtract these two terms, okay, which all of us can do in our head. 36 minus 1 is 35. So really, this equation is the same thing as y equals x squared plus 12x plus 35. So I just took a vertex form equation, multiplied it out to turn it into a standard. And going to Desmos, just going to show you that these two equations are the same. I'm going to graph it real quick. As quick as I can on a tablet. X squared plus 12x plus 35. And you'll notice, oh, look, if I go back and forth between my equations, they're identical. If you notice, they're right on top of each other, which just tells me that these two equations are equivalent. Okay. So this equation equals, I'll see, is the same as y equals x plus 6 squared minus 1. So that's a good way to check is you know you've multiplied this out correctly is if when you graph your original vertex form and your standard, you should get the exact same picture. If you haven't, go back and check your work, rework the problem, see where you made a mistake. Okay. Now, going into the last one, that Desmos is a good supporting tool. I'm not going to graph it again. I don't want to waste that time. So, order of operations here. If I have y is equal to negative 2, x plus 1 squared minus 4, parentheses, there's nothing in the parentheses for me to simplify. But I'm going to do the same thing I did last time with the exponent. I'm going to take this parentheses here, and I'm just going to break it apart into the two things that are multiplied together. So x plus 1 squared is the same thing as x plus 1 times x plus 1. And I bring down the negative 2 out front that's multiplying and the negative 4. Now, for the multiplication part, there's 3 things here really that were multiplied together. So it doesn't really matter the order in which you multiply them. So I'm going to still pick these 2 guys to multiply together first, and then I'm going to bring in this negative 2. So I've got to multiply all 3 of these guys together. Okay? So just pick 2 at a time. It doesn't matter what 2, and just multiply them. So I'm going to multiply these 2 guys together first. So the negative 2 is going to stay outside. Keep that in mind. I'm not multiplying it yet. But what I'm going to have is x squared plus 1x plus 1x plus 1 minus 4. This guy comes down. I'm taking my time showing all my steps. X squared plus 2x plus 1 minus 4. So I just combine my like terms. And now I can multiply that negative 2 in. And regardless of the order in which you multiply, you should get the same thing. Okay. So now I get negative 2x squared minus 4x minus 2 minus 4. And this is still y equals. Keep that in mind. I just don't write it every time. I can, though, for those of you that might need it. So now, what can I combine? Hopefully you answered. It's kind of to yourself. These 2 guys. Same as last time. It's pretty much the same order every time, which is nice. So when I do that, my final answer is going to be y equals negative 2x squared minus 4x minus 6, because negative 2 minus 4 is negative 6. And that's my final answer. Okay. So relatively short notes, guys. Nothing really to hit on. Just make sure that you pay attention to the steps. Okay. 2 examples of each to kind of, or for you guys to look at. Okay. If you have any questions, make sure that you refer to your teacher's office hours, whether they're doing online conferencing or just general email. But that's it for me, guys. Hopefully you enjoyed this lesson. Please feel free to reach out. If you'd like to keep my videos available to you and just keep tabs on them, you can like and subscribe this video. Okay. I'd really appreciate it. Thank you, guys. Have a good day.